So having introduced various components of the transmission electron microscope and seeing the emitters that we saw in the previous lecture, let us move on to the next component, which is also called as the heart of the microscope, which is your electron lenses. What you see here in this figure is a location of where the objective lens in a transmission electron microscope is located. Now, one important factor that you need to know here is the lenses used in electron microscopy can either be electrostatic or electromagnetic lenses. An example of the electrostatic lens is kind of the Venelt grid that you saw in the construction of a field emission gun or a thermonic gun. So essentially, when an electron beam is moving along the optic axis of the microscope, what you have is, under the influence of the electric and the magnetic fields, you would have a deflection of the electron beam. Let us try to look at what are the forces acting on a moving charged particle, in this particular case the electron, and then try to understand how the lenses behave, look at a few simple design of the lenses and understand the functionalities of this in this particular lecture. So moving on, the first point that I wanted to describe is what kind of force acts on a moving particle. Let us say I have a small charged particle and it is moving in an electric field. So if I apply a potential, this would tend to move in some trajectory as it goes down. It is not extremely accurate, but in the presence of an electric field, so let us say there is a charged particle with a charge q, and if the strength of the field is some E bar, the force acting on the particle is simply F bar is q dot E. Likewise, if I have a magnetic field, let us say I have a in plane or out of plane magnetic field like this. If I am representing the magnetic field coming out of the plane, when the same charged particle is entering this field, it starts experiencing some force here due to the presence of the magnetic field. This particular force is called the Lorentz force. Now, how do I quantify this Lorentz force? So, if I write m is mass of the particle, and let us say I use the radial coordinate system to describe the movement or the path of this particular charged particle, the force, which is mass times the acceleration, just going by the Newton's law to start with, is where nu bar or v bar is the velocity of the particle. It is a cross product between the velocity of the particle and the magnetic field. As you can see, for a particle, for the field which is coming out of the board and the particle which is moving down, I have a Lorentz force which acts on the particle based on this principle of deflection of the charged particle in presence of an electric or a magnetic field. People have come up with construction of electrostatic and electromagnetic lenses, which are used mainly in the electron microscopes. This idea of using an electromagnetic lens was first discovered by Bush in 1927, and Robert Knoll and Ernst Ruska used this principle to build the first working prototype of electron microscope in the early 1930s. So let us briefly have a look of how these lenses are and what happens to this charged particle. So like I was mentioning, if I look at the construction of an electron microscope, you have a kind of a cylindrical column along which you want to create an ultra high vacuum and you want the electron beam to propagate in this particular column. So if I draw a sort of a cross section, I have some kind of a construction within a microscope where the direction along Z is the direction where the electron beam is propagating, and I have the radial coordinate described by r here, and when an electron is moving downwards along the column of the microscope, it starts experiencing forces in the radial and the downward direction. So the magnetic field is typically along the axis of the microscope column, and also you have a radial magnetic field. So how do you get this kind of a magnetic field is if you typically use a current carrying conductor, let us say you have copper, if it is wound like a solenoid and there is a current flowing through this, what you have is a magnetic field created in the vertical direction, and within such a field created by a coil, if an electron or a charged particle goes through, it mainly experiences these two forces where you have the radial component and the vertical component. Under such a motion, if you look at the trajectory of the electron beam as well, here is a small simulation or an artistic impression of how the path of an electron beam within a magnetic lens looks like. I've just created this simply by entering the equation for Lorentz force and by applying a vertical magnetic field, assuming that the vertical component of the magnetic field is significantly more than the radial component. This is how the trajectory of an electron beam looks like. I've just entered this in a simple chat GPT and asked it to give an artistic impression of how the electron beam path is, and it came up with a reasonably okay-ish picture. So if I have copper coils here in which a current is passed, and the electron beam that goes in is actually now following this kind of a helical path. Just to give it a kind of a wave nature, they've also generated some kind of a sinusoidal or a periodic waveform here. But the point is, with the force that is actually acting, although this is not a very accurate description, when there is a current carrying conductor like a coil, which is analogous to an electromagnetic lens, the trajectory of the electron beam follows a helical path. Now, the exact derivation of the strength of the lens and the trajectory that an electron beam follows, you can always use some kind of more accurate calculations and sort of finite element method simulations to compute them. But for now, this is a reasonable picture, and what you have is different constructions of magnetic field coils, different constructions of coils which create an electromagnetic field, and with these in the electron microscope you can position them at different locations and then either squeeze this electron beam to a narrower point or you can stretch it. You can use coils which are perpendicular to the direction of the propagation of the electron beam. You can use combination of two coils which are called as dipoles. You can use quadrupoles, you can use hexapoles. There are multiple constructions of these kind of coils and arrangements, which is a combination of a current carrying conductor and a soft ferromagnet to simply apply a very high field. Typically, the strength of this field is anywhere between 1 to 2 Tesla, and with this you are kind of controlling the trajectory of your electron beam. Now, what is interesting is you can draw comparisons of a charged particle moving through an electromagnetic field to light propagating through a glass lens. So essentially, if I have a convex lens, when I place an object somewhere, and if there is a light ray traveling parallel to the optic axis, it converges at the focal point. In a very similar way, there are calculations which are done. There are something called as thin lens and thick lens approximations, which also show that similar to a convex lens in an optical microscope, the electromagnetic lens also within an electron microscope behaves in a similar fashion. By controlling the strength of the field that you are applying, which is, in other words, by controlling the current that is being passed through this coil, you can actually control the deflection or the point of convergence of the electron beam that is traveling within this particular electromagnetic lens. So, what you are changing by changing the magnetic field strength or by increasing or lowering the current is the point of convergence of the electron beam after the rays go paraxial to the optic axis. You are allowing them to converge either before the previous focal point or further away from the focal point. So essentially, you are also changing the focus of the magnetic lens by simply changing the field of the electromagnetic lens. With this, let me show you the electron microscope column again and a cross section of different kinds of coils that are there along the microscope column. So here is the 2100 microscope, and if you look at it, there are different kinds of coils which are placed here. There is a condenser or a stigmator coil. There is something called as a deflector. There is again another deflector here. There is a lens stigmator coil. There is mini lens coil, and there is another image shifter. There is intermediate lens, and of course here you have the screens. These are the coils that you have, and if you look at it, there is again the objective lens here. There is the condenser lens here. There is the mini condenser lens, and you have the beam deflection coils here. Now, when I talk about these coils and the names that are given to these coils, there are essentially two main actions that are happening in the electron microscope, which is when the electron beam goes along the axis of the microscope. I have not drawn the helical path, but bear in mind that this electron beam has a helical trajectory here. I would essentially like to do two actions. One is either deflect the beam in the, so let us say if this is my z axis, and at any given point, if I take a plane and I call it as the xy plane, so this plane could be either at the location of your condenser lens or at the objective lens or at your specimen plane, I would want my electron beam to be deflected in the x and y directions. This is one action that I want to do. And when I talk about the stigmator coils, I would want to have stretching of the image that is formed at each of these planes in the x and y planes. This is one of the actions that I want to do. So either I want to deflect the beam, or I want to stretch and elongate the beam, or I want to stretch and elongate the image that is formed by simply changing the trajectory of the electron beams by using different kinds of deflection coils. So by playing with the strengths of these coils, I can actually cause these possible actions. So either I deflect the beam, so I can use a beam deflection to also start causing rastering, which is one of the methodology of imaging where I want to form an electron probe and I scan from left to right in series like this, and I form an image by collecting the forward scattered electron. Or I also might want to tilt the beam. So there is something called as a pivot point in an electron microscope. So with respect to one fixed location, I want the beam to be tilted over some angle. So let me call it as some phi, for example, now. So these are the main actions that I want to do, either deflection, stretching, or tilting of the electron beam. So I achieve these by using different kinds of coils. So why am I telling this now is, from the previous slide, the image that I gave you is the construction of an electron beam of an electromagnetic lens is more or less like a solenoid or like a cylindrical coil. But you can also now, instead of having the coils stacked like this, I can stack a coil perpendicular to the plane of the perpendicular to the direction of the electron beam propagation. So these coils, I can have either magnetic dipoles, or I can have magnetic quadrupoles, or for some special advanced constructions, I could have hexapole or octopoles. So apart from simple cylindrical coils, which are the main electromagnetic lenses, I can also have octopole, hexapole, quadrupole, or dipoles, which have specific actions. Predominantly, the deflector coils are mainly dipoles, and depending on the direction of shift you want, you might also want to introduce a quadrupole as well. The tilting can be achieved with a dipole as well. So there are different functionalities for these, and different manufacturers use different configurations, but essentially the principle is all the same. So if I look at the schematic construction of the lens, what I'm getting up next is, this is how a general electron lens in an electron microscope looks like. So I've shown you the schematic. The circles here you see are all copper coils. So if you remember how a solenoid functions, if I write there are n turns in a solenoid, and I want to know the force that is acting because of the n turns in a solenoid, I can always write, if B is the magnetic field strength and I is the current passing through the coil, and if the total area of cross section of this particular solenoid is A, I can always get it as sum, and n is the number of terms. I can get the force as something of this form, which is again a simple expansion of the Lorentz force that I have written there. But essentially, based on the number of turns, you can also get the strength of the field here. So the idea is, when I have the coils perpendicular to the direction of propagation, that is, these are coming out of the plane and going in loop like this, I now have an electron beam and I have a magnetic field which is applied in the vertical direction as well. Please bear in mind that in construction of these kind of electron lenses, especially the electromagnetic lenses, because of the current passing through the copper coil, you would have resistive heating. You want to maintain the magnetic coil or the lens at a uniform temperature. You do not want to cause any kind of thermal expansion, which can in turn lead to some kind of instability. When you want to achieve resolutions as high as less than 1 angstrom, bear in mind, if the lens is maintained at 18 or 17 degrees centigrade or at the ambient conditions of the room temperature, I really need to circulate this chilled water. If you remember the lab layout and the demonstration video that I showed you, there's a chiller which is used to circulate the DI water through the microscope to cool these electromagnetic lenses at various locations. Unless you're maintaining the entire microscope column at an ambient temperature, you would have several problems. One of them is the thermal drift as well. Also, I was mentioning, if the chilling of the electromagnetic lenses or the chiller stops, the entire microscope also shuts down. It's a big problem. So you need to bear in mind that the chilled water supply is important to cool the lens from outside. So you're circulating cooled water to extract the heat that is produced from this and to maintain the entire column of the microscope at a uniform temperature. So, after that side note, again I'd like to bring you back to this particular design. So, here you see that there is a small bore in this particular lens. You have soft ferromagnetic material here. This is the pole piece of the lens. So, the idea is between these pole pieces, you are creating a magnetic field, and if I draw the magnetic lines of force here, they would have some kind of a shape like this. Okay. So, this kind of a construction is actually called as an immersion lens construction, and this was typically used in high voltage electron microscopes. And in these earlier designs of electron microscopes, which are operating typically beyond 1 million electron volt, or say even half a million electron volt or higher, the idea was by applying higher and higher accelerating voltage, I lower the wavelength of the electrons more, and I want to maintain this gap in this pole piece as small as possible. And the idea is you have this little pole piece gap because you want your specimen to be as close as possible to the objective lens to achieve as high magnifications as possible. So, if I draw a simple optical equivalent of a lens and I place an object at a distance, say d1, and let us say I want to bring this as close as possible to the focus, and if I say I am forming an image at a distance d2, I know that 1 by d1 plus 1 by d2 is 1 by f, and by bringing this d1 as close as possible to the focal length, I can achieve as high magnification as possible. So, if you look at it, the magnification, in other words, can also be written as d2 over d1, and the idea is if I bring this d1 as lower as possible, I can achieve as high magnifications as possible. And in the optical microscopes, you have something called as the working distance, where you are bringing the object as close as possible to the objective lens to achieve as high magnifications and in turn as high resolutions as possible in an optical microscope. But in an electromagnetic lens, because you do not have a physical lens but a field lens, what you are going to achieve is by immersing the specimen more or less in the field of the objective lens. So, by bringing this as small as possible and by reducing the focal length as small as possible and letting this d1 coincide with this f as much as possible, you can achieve very high magnifications. So, with this idea, the specimen is brought into the plane of the objective lens, and wherever the field strength is highest here, I can show you a little later that if I draw a nearly thin lens, the field can be approximated as concentrated maximum here, but if I have a thick lens, I can also give the field a near bell curve kind of an approximation. So, that means at this point where the field strength is very high, if I try to coincide the specimen as close as possible, you are at the right focus then and you achieve as high magnifications as possible. And on the other hand, when you are achieving extremely low wavelengths by increasing the accelerating voltage in the electron microscope, in the high voltage microscopes it was thought that if I have an immersive type of a lens and bring a specimen into the or if I immerse the specimen in between the pole pieces of the electromagnetic lens, I can achieve much better resolution. Resolutions as close as possible to 1.1 angstroms were achieved with this kind of a construction, but because of inherent lens defects, as you can see when I drew the magnetic lines of force here, when I get this gap in the pole piece, I would have a divergence in the magnetic field here, and when I do not have a uniform field distribution, this will have some consequences on the electron beam again, and they might not converge at a single point. This is again called as astigmatism, and because of these lens defects, you do not get very high resolutions. So this is one kind of a construction that was used, but when you have these kind of specimens which are immersed, when the pole piece gap is extremely small, typically for ultra high resolution lenses, the pole piece gap is much less than 2 millimeters. You are physically restricted with the rotations that you can do on a specimen. Bear in mind that when I want to image a specimen inside a microscope, I do not want to always image it static at one particular orientation. I want to tilt them to also get some crystallographic information. So with all these physical restrictions and with the improvements in instrumentation and electron microscopes, people move towards the more modern split pole piece type of a lens construction. So let me show you how the split pole piece design looks like. So in a split pole piece lens, unlike the immersion lens, you have a gap in between the pole piece. I have these kind of truncated conical structures which are pole pieces, again a soft ferromagnetic material. If I look at the physical image of how a lens looks like, this is an image taken from the Williams and Carter textbook again. I have two truncated cones of soft ferromagnets which act at this tip of the pole pieces, which are present at the tip of these pole pieces. So the idea is I apply a magnetic field again here, and by bringing this gap as small as possible, I want to confine the magnetic field as uniform as possible to minimize my lens aberrations. But with the invention of aberration correctors, people are now achieving more and more pole piece gap. This topic on aberrations I'll introduce at a little later stage, but before I go there, what I want to mention here is most of the modern day microscopes called as the intermediate voltage electron microscopes, which typically operate from 100 to 300 kV. There are also 30 kV and 50 kV configurations now possible. You would have the objective as a split pole piece lens, and you typically use a side entry holder, and this is one of the lens designs. If I look at only the upper part of this split pole piece lens, just the upper part here, you have a different construction called as the snorkel lens, which is typically used in an SEM. So in a snorkel lens, you have only one half. You have a conical pole piece here. It's a single pole piece, and you have a coil here. Of course, the coils to apply the magnetic field, and you also have the water supply here to keep the temperature of the lens uniform at one temperature. You also have the deflection coils, which look like the quadruple lens here, and you also have dipoles as well when you want to cause a beam tilt. Within a scanning electron microscope, typically a snorkel kind of a lens is used, and you have a combination of the other deflection coils, which also you have the condenser before this, and the idea is you want to converge the electron beam to a small probe, and by rastering the probe in X and Y directions by using the scan coils like I was mentioning some time ago, you form an image. So when the electron beam hits the specimen surface, you are collecting the signals that are generated, typically the secondary electrons or the backscattered electrons here, and by using different kinds of detectors, there is something called as the Everhart-Thornley detector for the secondary electrons. We'll look at it at a later stage. You can form an image in a scanning electron microscope. A similar principle is used in transmission electron microscope as well. You converge the electron beam to form a probe. You have a kind of a conical shaped probe, and you scan this, you raster it, and you're collecting the forward scattered electrons from a specimen, and you form an image in scanning transmission electron microscope. So Going back to the construction of an electron microscope again, there are series of these kind of coils. These are either dipoles or hexapoles or octopoles or quadrupoles, and each of them have specific functionalities, and the electron beam that is going in the electron microscope column follows a helical trajectory, and as a consequence of this kind of helical motion, when I change the strength of the field and when I change the magnifications of the lenses also, I see some kind of an image rotation that is happening. Now, the modern day microscopes in which you know when there is a change in the strength of the objective and the illumination lenses, when I switch from one mode to another mode, I can compensate for this rotation. But in the old school microscopes, even in this 2100 microscope, you typically end up seeing an image rotation. So I might start with imaging in an orientation like this. When I increase the magnification, I might end up with an orientation of your feature in this particular direction. So if I want to look at once again the physical image of how this split pole piece lens looks like, let me show you an example from one of our microscopes here. This is the pole piece that I was talking about. So here is your soft ferromagnetic material. These are made of brass, and you have the cooling water supply going from outside. You cannot get in water into the microscope column. So just by conduction, you want to extract the heat out, and with the convective flow of chilled water. This is all inside the microscope column, and it is all at the ultra high vacuum. But we opened up one of these ports here to just get an image of how the lens is. Now, why is this pole piece design and the pole piece gap important? One important parameter here is the magnetic field strength is going to vary as I go radially outward from the optic axis. But when I have this kind of a pole piece, the field distribution would change because there is a gap here. Now, this in turn introduces some lens aberrations. This is the first thing. The second thing is, physically, when I place a specimen holder into the microscope column, so from a side entry holder, if a specimen holder comes in here, I'm just drawing this not to the scale, but in this particular microscope, for example, I have holders which are of the width of 13 millimeters approximately. So if my holder design is like this, and this goes into a gap between the lenses here, this electron microscope holder can either rotate along this axis or along this axis. So this rotation or this rotation are restricted by the gap I have within the pole pieces. So physically, what consequence does this have is, when I want to do some kind of electron diffraction and get some crystallographic information from a material, I am restricted by how much I can tilt the specimen holder. So if the gap here is of the order of 2 to 3 millimeter for a high resolution pole piece, I am typically restricted to a tilt less than or equal to 15 degrees in one direction, and typically less than or equal to 20 degrees in the other direction. If the pole piece gap is of the order of 4 to 5 millimeters, I might end up with a tilt of plus minus 30 degrees and plus minus 15 degrees again. So the secondary tilt, which is perpendicular to the axis of the holder, this is either called as the beta tilt or the Y tilt, depending on the microscope manufacturer. This is always restricted to less than 15 or 20 degrees, because you do not want to crash the holder tip into the pole piece. And the primary tilt or the alpha tilt or X tilt is restricted with this diameter of the holder. There are something called as special tomography holders. Now, it is typically at a slightly higher price than the regular holder, which is not always necessary. If you manage to make just the tip of the holder at any local workshop, you might avoid paying an exorbitant sum to just buy a tomography holder. So the idea here is, by restricting the thickness or the width of the holder to a gap less than the pole piece gap of the microscope lenses that you have, you can actually achieve very high tilt and a larger range of tilts. So practically, these are quite important in understanding how the electron microscope construction is and how the split pole piece lens looks like, and why the holder is restricted to limited number of tilts and so on. So that is the information I have on the construction of lenses and the configuration of the modern day split pole piece type of a lens in an electron microscope, and the consequences of this on the tilt ranges. Now, what I'll do next is show you some basic equations and some basic definitions or basic concepts on the strength of the lens, and a few key terms that we use with related to the imaging that we typically do in electron microscope. Now, if I look at the general construction of an electromagnetic lens and look at the cross section, it approximately looks like this. I have the coils here, and my electron beam is going along this direction. If I call this as the Z direction, and I was mentioning that this has a helical trajectory like this. So if I say the fields here are like this, the magnetic field along the optic axis and along the radial direction, there is something called as the paraxial ray approximation, where the strength of the magnetic field along the direction of the electron beam is significantly higher than the radial component. Nonetheless, you cannot ignore this, but let us see, if I take the pole piece gap somewhere at this location. So here is where I have the pole piece gap, and I place a specimen here immersed within the field of lens, and if I call this as Z equals 0, just to start with, from the position where I have the optimum focus or where the specimen is positioned, the magnetic field strength is such that the magnetic field strength is such that you would want to have a maxima at the Z at 0, and the radial component, it kind of applies a force which is increasing and decreasing such that it makes it follow a helical path. So if I draw the variation of the magnetic field along the radial and Z directions, the field strength along the Z axis appears like this, and the field strength along the radial axis, it initially has a dip and then it goes to a maxima, and it goes minimal as I go far away from the lens. So if I say this is the field strength within this kind of a region, the radial component initially drops and it increases, and then it drops as I go far away. But the lens is designed such that I have a maxima at almost Z0. If I take a coil which has n turns, I can approximate the focal length is, if this pole piece gap here is some L, I can write it as 1 over L times 187 . So, the focal length is proportional to a sinusoidal form of the strength I am applying in the electromagnetic lens. So, if I draw the field distribution in such a configuration, so if I say here is my radial component and here is my longitudinal component along the optic axis of the microscope, around the pole piece gap, I typically have a field which looks like this. In such a configuration, here is the variation of the magnetic field in the radial and in the longitudinal directions, and here is how the lines of magnetic lines of force are represented. If I want to derive the focal length in such a situation, what I can do is I can take a magnetic scalar potential as a function of the 3 dimensions, and I take a Laplace equation of this del dot omega m r comma z is 0, and from this I can write a sort of a Taylor expansion of this as now. A similar expression can be derived for an electron beam which is propagating through a magnetic field like this, with the magnetic scalar potential which is given by these values, with which you can also obtain a expansion series of the phase shifts that are caused for the electron beam in terms of the angle of deviation away from the axis. So, this parameter becomes important when I am trying to understand the lens aberrations. We will come to that a little later, but essentially in such a field which is given by this kind of a magnetic scalar potential, if an electron beam enters, the force experienced by the electron beam can be written as and this has a form which is a sinusoidal kind of a waveform. And if I write matrix notation of this, the radial and the axial components of the forces and the magnetic fields can be written in terms of so from this, by using a few approximations, I can estimate the focal length and get a behavior of how my lens behaves, and there is something called as the thin lens approximation and the thick lens approximation, and there is also something called as the paraxial ray approximation. But from this I can simplify, and by taking a few modifications, there are detailed derivations on this available if somebody is interested. There are texts on this, and there is a beautiful article by Harald Rose where he talks about the magnetic field variations in the lenses in modern electron microscopes. You can refer to these, but what you end up with is an equation of this form. Focal length is and if I use a thick lens, I can give the magnetic field strength a bell-shaped potential, which is having seen how the magnetic field varies within the electromagnetic lenses. It is obvious that these are extremely sensitive and they're not as robust as the optical lenses, and these lenses are often defective. And how prominent are these lens defects is what we'll see in the next slide. So if you look at the common lens defects, when you take a regular optical lens, a glass lens, you have a problem called when there is a difference in the curvature of the lens on either side. So the radius of curvature, if it is not uniform, you often end up not converging the ray at a single point. This creates a kind of a distortion and you create a disk of confusion. If I say this particular problem is caused by the changes in the point of convergences due to unequal radii of curvature on either side of the lens, this kind of an effect is more pronounced in a thick electromagnetic lens where I have the bell-shaped kind of a potential. The electrons that are moving, which are perhaps not very coherent, there could be some incoherencies due to temporal or spatial coherency, or there might be some fluctuations in the high tension of the microscope. They would naturally not converge at one single point or one single plane. So this creates a disk or a sphere of confusion, and this is actually called as spherical aberration. So if I look at how perfect the lenses are, they are actually not perfect. If I physically fit in a value for this, the order of the spherical aberration is in the range of a few micrometer for an optical lens, whereas for an electromagnetic lens it is of the order of 1.2 to 1.5 millimeter. So the range over which the convergences can happen is very large, and as I was mentioning, this is orders of magnitude higher, and the origin of these defects is primarily the instabilities in the electron microscope high tension, the instabilities in the electromagnetic lenses, the fluctuations in the magnetic field. You can see that there are several magnetic field coils which are present all over the microscope column, and all of these together can create a lens defect called as spherical aberration. In fact, there are different kinds of aberrations in lenses, which in turn you can see that there is a change in the velocity of the electron beam which is going far away from the axis of the lens to something which is going very close, and they converge at two different points. What this does is it not only creates a spherical aberration, but there are different kinds of image distortions or defects which are created. And once we understand that this lens aberrations are also causing a phase shift to the electron beam, you can have an expansion in the form of a Taylor series and look at how the aberrations are and how the aberration corrections are done. This particular topic I'll revisit when we'll talk about the construction of an aberration corrector and how it functions. But before that, I would simply like to draw an analogy with an optical microscope and mention that if I have a lens, it is typically defective and it does not converge to a point, and if I give this disk of confusion a diameter, it has a form like this. So beta is the angle of deviation or the angle of convergence here, and this typically has I can write the lens aberrations in terms of the angle of deviation away from the optic axis, and when I expand it as a polynomial, the spherical aberration is the coefficient of the beta cube or theta cube here. So with this, I'd like to conclude that electron microscopes use electromagnetic lenses, and these are highly defective, and you have several lens aberrations, one of which is spherical aberration. There are different kinds of electromagnetic lenses. We've seen various designs. You have the immersion type lens, you have the split pole piece lens, you have the electrostatic lens, you have the snorkel lens, you have the dipole, quadrupole, hexapole lenses. Each of these lenses have different functionalities, and bear in mind that since these are electromagnetic lenses and the field strength is extremely sensitive to various parameters, these lenses are highly defective, and because of this, you do not achieve the optimum resolution closest to what you expect from the Raleigh's criteria in a transmission electron microscope. With this, I'd like to conclude this lecture.